Hey everyone, this is Mr. Weissert again. We're going to be going over some conditional probability and independence rules today. Let's get started. If you would like to follow along in your textbook, this is section 5.3 of the Practice of Statistics, updated 6th edition. And in AP Classroom, this will be covering topics 4.5 through 4.6. In my notes, it'll be Module 2, Lesson 3, which starts on page 140. So let's refer back to some previous data that we've learned. In the previous lesson, we talked about doing the eyebrow raise and the tongue roll, which I cannot do. And we have a couple questions to address. First, if we know that a randomly selected student can raise one eyebrow, what's the probability that the student can roll their tongue? In this case here, we're just talking about the ones that can raise an eyebrow. Out of those 62 people, how many can roll their tongue as well? That's going to be 42. So we're given the 62, and we're asked out of those 62, how many can roll their tongue? Of course, that'll reduce to a decimal if you want to write it like that, 0.6774. See if you can do the other one. If we know that a randomly selected student can roll their tongue, what is the probability that the student can raise one eyebrow? If you said 42 out of 149, you'd be correct, which gives you about 28.19%. This is what's called a conditional probability. In a conditional probability, we're always given something. So it's always going to be the overlap divided by what we're doing it out of. So it could be something like A given B or B given A, depending on the letters we use, and whatever really letter you want to use. Importantly, you're going to be using this symbol here, this vertical bar, to kind of distinguish what the word given is. So anything after that bar is what we're given. Anything before is what they kind of have in common. Let's look at an example. Example 1, in 1912, the luxury liner Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died, including Leonardo DiCaprio. The two-way table gives information about adult passengers who survived and who died by class of travel. Suppose we randomly select one of the adult passengers from the Titanic. Define events F, first class passenger, S, survived, and T, third class passenger. We got a few questions to answer, but importantly on this problem, it's good to have your totals before you do any of the work. So you want to go ahead and add your firsts, your second, your thirds, your survived, your died, and your overall totals. So that way we can work with those a little bit easier. So do that if you haven't done that. Second, find P probability T/S. What that means is the probability of T, which is third class passenger, given survived. Well, in this scenario, out of the ones that were survived, since we're given that, that's going to be 151 divided by 442, which is about 0.3416. So essentially 34.16% of the survivors were third class passengers. Part B, given that a chosen person is not a first class passenger, what's the probability that they survived? Write your answer as a probability statement using correct symbols for the events. I'm going to back up to A again. We were asked to describe the probability in words. So we would say, given that a randomly chosen person survived, there's about a 34.2% chance they were a third class passenger. Now on to part B. Well, first on part B, we want to write it in symbols. So it's the probability that survived given not first class. And we can use the complement symbol F with a little C if you'd like. So that's PS given FC, complement of C, or complement of F. And that's going to be the combined 94 and 151 divided by the combined 261 and 627. Because we're doing not first class, that means the second and third class. And that'll give you a 245 out of 888, which gives you about 0.2759. So about 27.59% of the second and third class passengers survived the Titanic. So just a couple of rules symbolically. On the AP exam, you're going to be given this formula in addition to the general addition formula that we learned in the last lesson. So These are what you see in symbolic form on your formula sheet. We want to be comfortable using them. And honestly, they're not that hard of formulas to know. So probably best to just have those remembered in your head. All right, another example. According to a recent survey, 70% of US teenagers use TikTok or Instagram daily. 63% use TikTok daily, and 59% use Instagram daily. Suppose we randomly select a US teenager. Given that the person uses TikTok daily, what's the probability that they also use Instagram? This may look familiar because we've did this before using Venn diagrams. So remember, in this problem, we're given that the person uses TikTok. So we want to set up a scenario. So since it's a conditional probability, we want to do what's the probability that they're an Instagram user given TikTok. So we'll write it like this. It'll look like what they have in common, the probability of Instagram and TikTok divided by the probability of TikTok. So we know that the probability of someone using TikTok is 63%, but we don't know the overlap. So we'll have to use that general addition rule we learned back in the last lesson and figure out what that overlap is. Recall that we're given, I'm going to use T and I, T for TikTok and I for Instagram to make this a little bit easier. We're given the 70% for or. So this right here is the or part. So we're going to go ahead and put that over here on the left side. And we're given the individual probabilities. What we'll do is we'll add those together and then we'll subtract. So if you do a little bit of math on that, which we've already did before, you get 0.52. So 52% of teenagers are both Instagram and TikTok users. Now we can kind of plug it into the formula. So since we're given the both, now we can put that on top of the 0.63 and divide. And so what you'll see is that 82.5% of the TikTok users also use Instagram daily. You might remember this Venn diagram, and you can kind of see in the Venn diagram that we have the 63% of the TikTok of the group as TikTok users. If you take that 52 and divide by 63, that's the percentage that this takes up. Not drawn to scale, of course. All right, let's look at this again. Now we have to ask the question, does knowing whether a randomly selected US teenager uses TikTok daily impact the probability of them using Instagram daily? And if you think about that, well, yeah, I mean, generally speaking, if someone is going to be using Instagram, they're going to be using TikTok, right? So there is some sort of relationship between those. So we've got to think logically first. Would we expect someone who uses TikTok that would also use Instagram? Most likely. Now think mathematically. What proportion of TikTok users use Instagram? What proportion of the sample uses Instagram? And what proportion of those who do not use TikTok use Instagram? You're going to get about 3 proportions you can get from the table here. 52 out of 63, that's the TikTok users that use Instagram. 59 out of 100 are just Instagram users in general. And 7 out of 37 are the non-TikTok users who use Instagram. And as far as for events to be considered independent, we would want those numbers to be the same. Now, in this case here, there's a big difference between the proportion of students, TikTok users who use Instagram, the proportion of non-TikTok users who use Instagram, and the proportion of Instagram users in general. You can see they're all different. So the general rule for independent events is if you don't get close to the same, I mean, for our purposes, we'll just use exactly the same. But if they're not the same value, then they're not going to be independent of each other, which means that there is a relationship between those things, between Instagram and TikTok users. Independent means there is no relationship. One doesn't affect the other. So let's think about a few examples. Stephen Curry is a 91% free throw shooter. He takes a free throw shot, waits, then takes another. Would you consider that independent? Yeah. The shots shouldn't have an impact on each other, especially if you're given wait time between them. How about rolling a 6-sided die 3 times in a row? That's also independent. Die have no memory, so each roll shouldn't impact the next. A bag has 15 blue marbles and 10 red marbles. You randomly select a marble out of the bag, keep it, then randomly select another marble. Well, in this case here, we're sampling without replacement. So we're not putting it back. The probability is going to change. They're not independent. Selecting a random time of day and asking somebody if they are tired. Well, if it's really, really late at night or early in the morning, they might be tired. I would say they're not independent. Time of day likely impacts that. And then the last one, selecting a Scrabble tile out of a bag, replacing it, shuffling the bag, and then selecting another. In this case, that's going to be independent because when you replace it and you randomize the selection again, that's going to keep it the same probability. Let me take my face off of there for a second so you can see that. Okay. Another way to look at independence is thinking about what a segmented bar graph might look like if they were truly independent of each other. Now, as you can see, there is a relationship here. In fact, the percentage of TikTok users who use Instagram is pretty high, and the percentage of non-TikTok users who use Instagram is pretty low. But if they were truly independent, what would this table look like? How could you get these numbers here? Well, we'd want to take the total percentage, 59% of 63, and get these numbers. Now, these are decimals. I'm not going to round or anything, but that would give you 37.17, and 41% of 63 is 25.83. You do the same thing for the non-TikTok users. You do 59% of 37 and 41% of 37. And if you were to make a segmented bar graph using the relative frequency, you would notice that they would be the same height for the percentages that use Instagram, because both of those should be around 59% for the Instagram users and the rest of it, the 41% for the non-Instagram users, regardless of whether or not they use TikTok. So just kind of see visually what that looks like as a graph. If they were independent, we'd expect the relative frequencies to be exactly the same. All right, here's a check your understanding. Yellowstone National Park surveyed a random sample of 1,526 winter visitors to the park. They asked each person whether they belonged to an environmental club, like the Sierra Club. Respondents were also asked whether they owned, rented, or had never used a snowmobile. The two-way table summarizes the survey responses. Suppose we randomly select one of the survey respondents. Define events E, environmental club member, S, snowmobile owner, and N, never used. A, find probability N given E. Describe the probability in words. Well, probability N given E is out of the E environmental club, that's 212 never use a snowmobile out of 305. That's about 0.695. And we can say, given that a person surveyed belongs to an environmental club, there's about a 69.5% chance they never use a snowmobile. Part B. Given that the chosen person is not a snowmobile owner, what's the probability that they are an environmental club member? Write your answer as a probability statement using correct symbols for the events. So we're given that they're not a snowmobile owner, which means that it's one of these two here, 657 or 574, never or rent. The probability that they are in an environmental club from those are going to be these 212 and 77 divided by the overall here. So that's going to look like this: 212 plus 77 divided by 657 plus 574. We'll want to add the tops and bottoms separately, and you'll get about 0.235. And then finally, are the events snowmobile owner, environmental club member, independent? Justify your answer. And in this case here, if you just do a few divisions here, and you can kind of stick along the same direction, the probability that they're a snowmobile owner in general is going to be 295 out of 1526, so about 19.3%. But the probabilities change drastically if they're an environmental club member or not. So look at the environmental club members, 16 out of 305, only 5.2% were snowmobile owners, whereas the non-environmental club members, it's a much bigger percentage, 279 out of 1221. So that's about 22.9%. So since those are all different, we would say that they're not independent. In other words, knowing that somebody is an environmental club member will impact whether or not they own a snowmobile. Let's look at just the general, how we can find the ands. There's going to be some situations where we're not given that, but we'll need it to figure out certain probabilities. So let's look at this situation. About 55% of high school students participate in school athletic team at some level. Roughly 6% of these athletes go on to play on a college team in the NCAA. What percent of high school students play a sport in high school and go on to play on an NCAA team? So in this scenario, you want to think about the conditional probability rule. So the probability of NCAA team given high school sport is the probability of NCAA team in high school sport out of the probability that they're just a high school sport player. Now, we're actually given two of these three things. Okay, we're given this 6% here is actually, since it says roughly 6% of these athletes go on to play on a college team in the NCAA, that's what the conditional probability is equal to. So 6% of the high school sport players play in an NCAA team. Now, that 55% is just the percent of students who participate in a school athletic team. So to get the and, this is just an equation. And at the end of the day, we just want to multiply these numbers together. So we're going to multiply the high school sport and the conditional probability NCAA team given high school sport. And well, we'll get 0.55 times 0.06, which is 0.033, which represents the probability that they're on both an NCAA team and played a high school sport. And that's the general multiplication rule. In this case here, we just want to multiply any events together, being mindful of if their probabilities change due to it being a conditional probability. Here's a scenario. This is example 3. We got some starbursts. So we have 6 red starbursts in a container and 4 yellow. Suppose we randomly select 2 candies from the container. What's the probability that both are red? Well, and the probability that both are red, the first is red and the second's red. Now, if the first is red, I'm going to have 6 out of 10 to choose from. So it's going to be 6 out of 10. But if I take another red out on my second try, it's going to be, well, let's see if that's gone. I only have 5 out of 9 now. So that probability is going to change when I remove one. So you'll do 6 out of 10 times 5 out of 9. Use that general multiplication rule. Multiply straight across, just like any fractions. It's going to be 30 over 90, which you can reduce to 1/3 or 0.333 if you'd like. Well, how about part B? What's the probability that they're both yellow? You're going to do the same thing. Although in this case, if we're going to take a yellow out, 4 out of 10 is going to be your first draw, but only 3 out of 9 on your second draw. So when you set that up, it's going to look like first yellow, second yellow, 4 out of 10 times 3 out of 9, which is going to be 12 out of 90, which will give you about 0.1333. In this scenario, it's helpful to make a tree diagram to be able to see all your different outcomes for probabilities. So when you're doing those, you want to first think about your initial thing. You're going to first make one draw, and it's either going to be a red or a yellow. So that first draw, 6 out of 10, 4 out of 10. Those should add to 1. Now on the second draw, depending on where you're coming from, if you've taken a red, then you're going to have only 5 reds left, and that'll be 5 out of 9 to get the second red. To get that second one being a yellow, that's actually going to be, you'll still have all your yellow, so it's going to be 4, but you'll still have 1 less number overall, so 4 out of 9. Same thing with the yellow. If you drew a yellow, you'll have all your reds, so it'll be 6 out of 9, and then you'll only have 3 yellows out of 9 in your second draw. Now, at the end of your tree diagrams, you always want to multiply those probabilities together, because out here represents your ands. And they also should add to 1. So all 4 of these, 30 plus 24, 24, and 12, those numbers will add to 90. Now, this will help us answer a few questions. So let's look at this again. Part C, what's the probability of winning this game? So winning means you get both red or both yellow. Well, you can get both red 30 out of 90 times, or you can get both yellow 12 out of 90 times. And since we're using the word or, we're going to add those together, and you're going to get 42 out of 90, or about 0.4667. So the probability of winning this game is about 46.7%. Given that the person wins the game, what's the probability that both candies are red? Well, given that they won the game, let's look over here again. The probability that both candies are red, if we look at, we've already calculated the probability of winning the game. So that's going to be your given. That's going to be at the bottom of your fraction. And at the top of your fraction, the probability they're both going to be red is going to be 30 out of 90. So that's just going to be 30 out of 90 over 42 out of 90. Now, in this scenario, the 90s actually cancel out. So you can just do 30 out of 42, which is about 0.7143. So in other words, if you won, chances are 71.43% of the time you got red both times. Now, part E, given that the person wins the game, what's the probability that both candies are yellow? Well, what's left over? In this case here, it's going to be the same denominator because winning the game is still going to be 42 out of 90. But in the case of both yellow, we're only talking about 12 out of 90. That's 12 out of 42, which is about 28.57%. Should note that these two are your only options for winning the game, and those two should add to 1 if you did this right. All right, let's look at this check your understanding. Many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't, a false positive. Other times the test says that a woman doesn't have breast cancer when she actually does, a false negative. Suppose that we know the following information about breast cancer in mammograms in a particular population. 1% of the women aged 40 or over in this population have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. Question: a randomly selected woman aged 40 or over from this population tests positive for breast cancer in a mammogram. Find the probability that she actually has breast cancer. There's a lot going on in this scenario, so the best thing you want to do in this case is set up a tree diagram. Pause the question, see if you can make a tree diagram based on the information. Then unpause it, and I'll go over it. All right, let's take a look at all this here. We'll kind of set it up. There's a lot going on here, so let's see if we can break it down. In this case here, we're given 1% of women age 40 or over have breast cancer. So notice that I put the 0.01. So we have to subtract that from 1 to get the 0.99 that do not have breast cancer. The next thing is, for women who have breast cancer, the probability of a negative mammogram is 0.03. So a negative mammogram is 0.003 for those who have breast cancer. And then we can subtract that from 1 to get the 0.97. Same thing with the bottom one. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. So we have the probability of positive mammogram for those who don't have it. Subtract that from 1 to get the 0.94. At the end, always multiply along your branches. So 0.01 times 0.97 is going to be 0.0097. And you can go through and do all of your ands. Now let's look at the question. We randomly selected a woman aged 40 or over from this population. Find the probability that she actually has breast cancer. So we're talking about 40 or over from this population who test positive for breast cancer. So we're only really worried about the ones that test positive in this probability scenario. So just looking at that one and that one. Out of those two, the probability that they're going to actually have breast cancer is going to come from this branch. So the 0.0097 will be on the numerator because that's kind of the overlap. That's kind of what they have in common. And then both of these will be on the denominator because that's all of the possibilities that have a positive mammogram. And so if you divide 0.0097 by the sum of these, which is 0.0691, you get about 0.1404. In other words, the probability that a woman has breast cancer, given that she tests positive, is only 14%. And that's not too good, actually, is it? But that's the answer to this question. So let's look on to the next example. Before we do that, I just want to see if you can think about how to take that tree diagram and convert it into a table, a two-way table of values. Sometimes that makes it easier for people. So here's the scenario again. And let's assume we have 10,000 women in this case to make our calculations easy. I want to show you the numbers that I got, and let's see if you can figure out where they came from. So the positive and yes, that's going to be the 97. You can see that 97, 0.0097 times 10,000 is going to get you that. And actually, all four of these numbers are going to come right from the ands over here. And so now you can get your totals just by adding them together along the rows and the columns. So just something interesting to think about. If you ever are wondering how to make that a little bit more readable, consider doing a two-way table if you have the time. All right, the multiplication rule for independent events is pretty straightforward. If they're truly independent, then you can just multiply them together. So if I roll a die once and I roll it another time, 1/6 times 1/6, the probability of getting 2 ones, for example. So conditional probability has no factor here. Let's look at these questions. Suppose Pedro drives to work, or drives the same route to work on Monday through Thursday. His route includes one traffic light. The probability that the light will be green when Pedro arrives is 0.42, yellow 0.03, and red 0.55. Question 1, what's the probability that the light is green on Monday and red on Tuesday? Well, these are independent events, so we can multiply those together. So the probability that it's green on Monday is 0.42. And the probability that it's red on Tuesday is 0.55. We'll multiply those together to get 0.231. Question 2, what's the probability that Pedro finds the light red on each of the days from Monday through Thursday? So again, they're all independent. So probability of red is going to be 0.55 times 0.55 times 0.55 times 0.55. You can use an exponent if it's easier. 0.55 to the fourth power will get you the same answer, which is about 0.0915. Question 3, what's the probability that he finds the red light on at least one of the days from Monday through Thursday? This one's a little tricky, but at least one is the same as the probability that there are no reds subtracted from 1. So the probability that none of them are red is going to be 0.45 to the fourth power instead of 0.55 to the fourth power where all of them are red. So it should make sense that if I want to know the likelihood of at least one of them being red, then that's going to be everything but the probability that none of them are red. So we can subtract that 0.45 to the fourth power from 1, and you'll get 0.959. So 95.9% of the time, there's going to be at least one red. Let's look at this more formally. Example 4. On January 28th, 1986, the Space Shuttle Challenger exploded on takeoff. I was 6 years old. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under the cold conditions that day, experts estimated that the probability that an individual O-ring would function properly was 0.977. But there were 6 of these O-ring joints, and all 6 had to function properly for the shuttle to launch safely. Assume that O-ring joints succeed or fail independently. Find the probability that at least one of those O-ring joints fails. So the first thing we want to do is what we're trying to figure out is the probability 1 in 6 O-rings fail. We know that the probability that one O-ring works is 0.977. The probability that all 6 work is 0.977 to the 6th power. The probability at least one O-ring fails is going to be 1 minus the probability that none of the O-rings fail, which is the same as 1 minus the probability that all 6 work. So we can do 1 minus 0.977 to the 6th power, and you'll get about 13.03%. So if you think about that from a safety aspect, that's a 13% failure rate for this mission. So it's no wonder that this happen. I mean, that wasn't a very small chance. So the likelihood of that happening was pretty large in this case, when we're talking about human lives anyway. Example 5. Hacienda Heights and La Puente are two neighboring suburbs in the LA area. According to the local newspaper, there's a 50% chance of rain tomorrow in Hacienda Heights and a 50% chance of rain in La Puente. Does this mean that there is a 0.5 times 0.5 equals 0.25 probability that it will rain in both cities tomorrow? No, these are not independent. See, those locations are both in the LA area. It's likely that if it's going to be raining in one of those locations, then it's going to be more than a 50% chance of it raining in the other. So we're not going to multiply events if they're not independent. Do a little practice with independence, just using the probability rules. So here's letter A. If A and B are independent and the probability of A is 0.6 and the probability of B is 0.8, what is the probability of A or B? Well, let's look at this multiplication rule again. If we know that they're independent, then we can multiply them together. So the probability of A and B is going to be 0.48. Now what we can do is we can take that away from the sum of the two probabilities. The general addition rule, just add up their probabilities and subtract their overlap. That's going to be about 0.92. Part B, suppose that probability of A is 0.45 and the probability of B is 0.35. If the probability of A or B is equal to 0.62, are the A and B independent events? If they're independent, then the multiplication rule should kick in, so you can multiply 0.45 times 0.35 and get 0.1575. But let's actually look and see if that actually matches up our equation. So we're going to use the general addition rule again. We're going to plug in our or and our two individual probabilities. Now we're going to put in that 0.1575 to test to see if that actually makes the equation true. So we'll add the 0.45, 0.35, and subtract the 0.1575. In this case here, they're not the same. Since they're different, that means they're not independent. They're not equal to each other. Now you can go back to that Instagram TikTok table and think about it using this multiplication rule if you wish. What you can do is you can say, well, I know that if they are truly independent, then 59% times 63% should equal 52%, but it doesn't. See, if I do 0.63 times 0.59, I'm going to get 0.5. I'm not going to get 0.52. I'm going to get 0.3717. So that's another way you can test to see if events in a two-way table are independent. All right, to end this, we have 3 check your understanding questions. Thank you for hanging in with us. This is a long one, so I appreciate your time. So read those questions, pause the video if you want to, and try them all out on your own. Question number 1. New Jersey Transit claims that its 8 a.m. train from Princeton to New York has probability 0.9 of arriving on time. Assuming that this claim is true, what's the probability that the train arrives late at least once in a 5-day week? Well, in this case here, we want to assume each day is independent. So the probability of being on time is 0.9. The probability of all 5 days being on time is 0.9 to the 5th power. We want to know what's the probability of at least one time being late in those 5 days. So probability of late at least once is the same as 1 minus the probability that all days are on time. Since we calculated 0.9 to the 5th power, we can subtract that from 1, and we'll get an answer of 0.40951. In other words, there's a 40.95% chance of being late at least once during that 5-day week. Question 2. Government data shows that 5.4% of adults are full-time college students and that 37.8% of adults are age 55 or older. If we randomly select an adult, is it true that the probability of full-time college student and age 55 or older is equal to their product, which is 0.02? Why or why not? Well, this is no. These aren't independent. Knowing that a person's full-time college student is going to decrease the likelihood that they're going to be an adult age 55 or older. Question 3. A computer company makes desktop, laptop, and tablet computers at factories in 2 states. California, and Texas. The California factory produces 40% of the company's computers, and the Texas factory makes the rest. Of the computers made in California, 25% are desktops, 30% are laptops, and the rest are tablets. Of those made in Texas, 10% are desktops, 20% are laptops, and the rest are tablets. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from a distribution center and observe where it was made, whether it is a desktop, laptop, or tablet. Question: given that a tablet computer is selected, what's the probability that it was made in California? This is a tree diagram problem, so we can set it up as maybe two different sections. First, talking about the state, California or Texas, and whether or not it's a desktop, laptop, or tablet for each state. Now, we're given a few different percentages. I'm going to take this one out for a second. We're given the California's percentage is 40%. We're given the desktop and laptop percentages from California, and we're given the desktop and laptop percentages from Texas. We're going to have to subtract from 1 to get the remaining for each of those branches. Next, we want to do our ands. Now, in this case here, it says we were given that a tablet computer is selected. So I'm really only focused on the tablets here. Now, you can do all the ands if you want, but 40 times 0.4 times 0.45 is 0.18, and 0.6 times 0.7 is 0.42. I'm going to focus on those two numbers because the question says, what's the probability that it is going to be a tablet, it's going to be made in California, given that it's a tablet computer? Well, so we're given that it's a tablet computer. We're given these two numbers here. That's your denominator. The numerator is just going to be what percent, which one is going to be from California. It's going to be that 0.18. So 0.18 divided by the 0.18 plus the 0.42 is going to be 0.18 over 0.60. That divides to 0.30. In other words, 30% of the tablets from this company are made in California. All right, let's summarize what we learned. First, conditional probability is the probability of an event happening given another event has happened. We can see the symbols to use in the formula. Independent events are knowing whether or not one event has occurred does not change the probability that another event happens. For them to be true, we want that the probability of one event being the same as the probability of that event given another event, and the probability of that event given the complement of that event. Tree diagrams are useful when you have multiple stages to work with. They display the sample space. Often we use it for conditional probabilities. Don't forget the ands at the end. The general multiplication rule means that you're going to multiply the probability of something and the probability that the next thing happens given the first thing happens. So the general multiplication rule takes into account conditional probabilities. If the probabilities are independent, you can straight up multiply them together, and there is no conditional probability to contend with. Well, that concludes our lesson. It was a long one. I appreciate you hanging in there, and thanks for watching.